Hello, everybody. Thank you for joining us tonight. I'm Jared,
I'm Destiny.
I'm Andrew.
And I'm Courtney.
and tonight we will be talking about geometric figures. We're going to start off with you, Destiny.
All right.
First, does the corresponding angles property take place within the figure?
Let's see. In order to answer your question, Jared, I think it's important for us to understand a few definitions before we get started. So according to this figure, we have two parallel lines that are labeled as lines 1 and 2. Now, parallel lines, this means that they're never going to touch, they're never going to cross, and they'll never intersect, but they will be an equal distance apart from each other forever. Now, there's two other lines on this figure, the crisscross ones that form an X, and these are called transversal lines. Now, the definition of a transversal line is a line that crosses past two other lines, and sometimes those two other lines are parallel lines like we've got here in our problem. So therefore, the corresponding angles property does take place within this figure, because if two parallel lines are cut by one or two transversal lines, then the pairs of corresponding angles are always congruent. And this means that their angle measures will be the same. So next, I've got a question for you, Andrew.
Okay.
What are the corresponding angles that we just saw in that last figure?
That's a good question. Very good question. All right, so I'm going to pull this graph up right here. It's very similar to the one that you were just talking about. Corresponding angles are the angles which occupy the same relative position at each intersection where a straight line crosses two others. So if the two lines are parallel, the corresponding angles are equal. With that being said, we have a few in this figure that actually correspond with each other. And the first ones are 1 and 7, right here, that correspond to each other. And then we have angles 3 and angle 61 right down there at the bottom left part of that inner triangle. And then angle 4 and 9 right there as well. And angles 5 and 12 correspond as well. So these are the corresponding angles within this figure. And Jared, I have a question for you, bud.
Go for it.
What are the complementary angles? How do they relate to supplementary and similar angles?
Good question, Andrew. Let's start by focusing on complementary angles. A complementary angle is an angle where the pair of angles that come together, to form a 90-degree angle. Now, this is usually added up taken either from a 90-degree angle by itself or by adding two or more angles together. Now, how does this relate to supplementary and similar angles? I'll demonstrate for you. We'll have a parallel line here and a transversal that cuts through that parallel line. Now, in this case, you'll have two sets of similar angles, one horizontally and one vertically. We'll point that out for you here. And with that in mind, a supplementary angle is an angle where they're added up to 180 degrees. And by looking at this parallel line, you can notice that going from one end to the other part of the parallel line, you take 180 degrees to go from that point in a circular manner. You'll repeat this for the bottom half of the parallel line as well. So with that being said, you don't typically get a 90-degree angle in this setting. So as a result, we had no reasons to show complementary angles in this problem. So to give you an idea with numbers, if this angle right over here was 50 degrees, then this other angle here would also have to be 50 degrees since they are adjacent to each other and therefore hold to the same values. Also, this tells us since that we need half of the upper and lower half of the line need to be 180 degrees. This tells us that the black angles over here are 130 degrees. which allows them to add up to 180 degrees for half of the line and 360 degrees for the whole circle. Thank you for asking. Courtney, I have a question for you. How would you classify triangles such as the scalene, the isosceles, and the equilateral triangles?
You can see that I have 3 different triangles on this slide. Let me move it to the next slide. And this first triangle, you'll classify it by, you can see that 2 of the sides of the triangle are equal to each other. And this will make it an isosceles triangle. The next triangle, you can see that it has a right angle, making it a right triangle. And my last triangle, you can see that the 3 sides of the triangle, none of the sides are equal in length, so that will make it a scalene triangle. Okay. And next we have a question for Destiny. Destiny, can you tell me which angles are supplementary within this figure?
Of course. Thanks for asking.
All right. Hold on. All right. Do you have it?
I believe so. There we go.
All right.
Thank you.
You're welcome.
So to answer your question, Courtney, supplementary angles are angles they can be 2 or 3 angles, and their measures add up to equal 180 degrees. And sometimes those 2 or 3 angles, they can form a linear pair or even a straight angle, which looks like a straight line. Now, a straight angle, it also has a measure of 180 degrees. Therefore, we can just look at this figure and we can see which angles form a straight line, or in other words, a straight angle. So we can definitely see that angles 2 and 3, they form a straight line. Angles 4, 5, and 6 form a straight line, and angles 7 and 8 form a straight line as well. So therefore, all of those angles are going to measure up to equal 180 degrees. Okay, Andrew, what are the measures of the supplementary angles in your question?
In order to figure out all of the supplementary angles, we need to begin by finding angle 1. So here's a little graph. Here's a little graph right here. And according to the angle sum and a triangle definition, the sum of measures of 3 interior angles of a triangle is 180 degrees. Therefore, we need to subtract 26 degrees, 74 from 180, and we get 80 right here for angle 1. Now that we know this, we can also solve for angle 3 right here. Since angle 3 is congruent to angle 1, this would make it 80 degrees as well. And right here, we can also see that number 2 is 100 degrees, because all we have to do is subtract 80 from 100 degrees, because this is a straight line, and a straight line would equal 180 degrees. So all we have to do is just do that subtraction and get that 100 degree right there. So, and since angles 2 and 3 are supplementary, we can subtract 180 degrees from 80, like I had already previously said. But moving on, now we can figure out what angle 4 is. Well, angle 4 is right over here, point Q, angle 4. If we just subtract 180 from 80 from 180, which is angle 3, minus 74 degrees at point C, we would simply get 26 degrees. And next, we can figure out that right here, we get 80 degrees at point 5, because you can either add these two up right here, subtract them from 180, get it right here, or you can just subtract 180, subtract 26 and 74 from 180 separately, and we would still get this right here. And to figure out angles, let's see, rest 60s. Angle 6, we have 74 degrees. Angle 8, we have 80. This is very similar to how we figured out point Q, angle 4 right here for 26. We just, like I said, the interior of a triangle, we'd try to have to equal up to 180 degrees. So we just go ahead and either add these two up right here and subtract, add these up right here, subtract them from 180, and we'd get 180 for angle 8. And for 7, since it's congruent to 2, it'd also be the same angle right here for angle 7. So that answers your question, what the measures are for the supplementary angles. And now, Jared, I have a question for you.
Go for it.
How does a traversal create similar angles with parallel lines?
Good question. All right. Let me show. Let's get out the lines. Let's get out the lines again. So let's say, first of all, let's understand what a transversal line is. First of all, if you have two sets of parallel lines, then the transversals are the lines that cross both the parallel lines, and in the specific case of the problems, they intersect with each other here at line 1 to create these angles. So the question here is, how does it create similar angles? Well, look at here. It intersects the lines and it creates these little pockets here. We can label these as angles. Let's call, for simplicity, let's call them angles A, B, C, A, B, and C. Now, similar angles are adjacent to each other. So angle C, well, look over here. That angle is adjacent to this angle, and therefore both of them are angle C. Angle B is going to be, the angle B that is adjacent here is also going to be angle B. And likewise with A. Now, we can apply this to the other two line intersections that we have here. Like, for example, see how C and angle C are adjacent to each other up here? This transversal here actually has the same angle when it intersects both parallel lines. As a result, angle C is going to be represented here as well, since it fits in the same pockets in the transversal. Likewise, with the line over here on the right, angle A is represented here and here. This will yet again be represented with this transversal, since this transversal has the same angle with both parallel lines. Thank you for that question. Right, Courtney, I'm going to turn it back to you. How do you calculate the angles of a n-gon, a polygon with n sides?
Well, first we would need to count the sides, and you can see that when you count the sides, 1, 2, 3, 4, 5, 6, there's 6 sides. So 9 is equal to 6. And then we will use the interior angle equation, the exterior angle equation, and the central angle equation to figure out the degree of the angle. So for the interior angle equation, we will plug in 6. So 6 minus 2, multiply by 180, and divide by 6 to get 120. And that is this interior angle. Oops, hang on one second. Let me get the pointer. Okay. This interior angle. Uh-oh.
Nope.
Okay. Sorry.
It's okay.
Okay. This interior. Oh my gosh, what has happened right now? 1 second. Okay. This interior angle. And then to find the exterior angle and the central angle, you're going to use the same equation, so they're going to equal the same degree. So we'll have 360 divided by n, so plug in 6 for n, and you'll get 60, and that'll equal your interior angle and your central angle. Okay. Next question for Destiny. How do you find the sum of angle measures within the polygon?
Well, let's see. Let me pull up the figure real quick.
All right.
There we go. So the sum of the measures of the interior angles of any polygon within sides will be n minus 2 times 180, and n equals the number of sides you have in your polygon. So after you count these, we've got 1, 2, 3, 4, 5, 6, 7, 8. Sorry about that. And our equation will be 8 minus 2 times 180 degrees equals 1080 degrees. And once you've done that, we're going to just set up all of our interior angles equal to 1080 degrees. And that's what this is over here. So I'm going to move us over here for a second. So once we've done that, we've got 3y plus 7y plus 7y plus 7y plus 3y plus 12y plus 12y plus 3y equals 1080 degrees. And once we simplify the left side, we get 54y equals 1080 degrees. And then once we divide both sides by 54, we get y equals 20. And now you can substitute your y into each of these interior angles that have the y. So when we do that, we will get, we'll get 3y, which is 3 times 20 equals 60 degrees. So that means that each of our 3 y's are going to be 60 degrees. 7y equals 7 times 20, and that'll equal 140 degrees. So each of these will equal 140. And then 12y equals 12 times 20, and that will equal 240 degrees, which are these two angles right here. So that is how you find the sum of angle measures within this polygon. So I'm going to ask Andrew the next question. What are some other examples of polygons?
Yes, there are many, many other polygons out there. A polygon, pretty much what it is, it's a plane figure with at least 3 straight sides and angles, typically 5 or more. And here we have one right here. It's a right triangle. We simply have one side right here, one straight side right here, and one straight side right here. And we have the triangle, and there's also an octagon. We have an octagon that has 8 sides and 8 different angles that have 8 particular angles. Some other examples are like squares, pentagons, hexagons, concave octagons, and the list could go on and on and on. So these are some of the other examples of polygons. Just remember that it's a plane figure with at least 3 straight sides and angles, and typically 5 or more. And the next question is for you, Jared.
All right.
Could you explain why 180 degrees is used as a basis for finding the angle values in question 2?
Sure. All right. Well, let's start by thinking about the question itself. It's a triangle. We know that a triangle, all 3 angles in that triangle add up to 180 degrees. So we started off with 26 and 74 degrees. So when you add those up, you get 100 degrees, which leaves only 80 degrees to get your final answer of 180 degrees. And that's going to be the key here, because when our lines come in, you'll notice that all of the other angles that would be used that you needed to find the problem all could be broken off into its own little triangles. And as a result, you would use the concept of a triangle being 180 degrees to fill in the rest of the spaces. So overall, 180 degrees is important because that's how many degrees there are in a triangle. And as long as you remember that, you'll get through that question with no problems. Courtney, we're going back to you. How can you determine the measure of angle E if line AB and CD are parallel?
First, you'll see that we have two parallel lines, line AB and line CD. And okay, there you go. So we're going to extend the line on from E right here, line G, and we have the measurement of angle A, 121, and angle C, 134, and we're going to use those two angles to find the measurement of E. The three angles should add up to be 360, so we will add angle A and C together to get 255 and subtract it from 360 to get 85 for angle E.
Good job.
Thank you.
You're welcome.
Our next question is for Destiny. Destiny, why is the sum of measures of the exterior angles in this figure equal to 360?
That's a great question, Courtney. Let's see if we can pull up that figure. Here it is. So let's think about that question. According to the sums of the angle measures theorem in a convex polygon, we know that each of the exterior angles, and these are just a few of the exterior angles, but it will go all the way around the polygon. That theorem states that each of those exterior angles are going to have a sum of 360 degrees. So added together, they're all going to equal 360 degrees. So starting at this vertex right here, imagine walking all the way around this polygon. So as you're walking around, you're passing through an exterior angle at each vertex. And towards the end of the walk, we get to the very beginning, the vertex where we started, and that means that we made a full 360 degrees around the whole entire polygon. So that means that we can divide 360 degrees by the amount of sides that our polygon has. And as we were walking around our polygon, we realized that it had 9 sides. So we would just plug in 9 for n right here, and that would give us the equation 360 divided by 9 equals 40 degrees. So that means that each one of these exterior angles is going to equal 40 degrees. And all of those together will add up to equal 360. So thank you for asking. I've got a question for you now, Andrew. What are the interior angles inside of this 9-sided polygon?
Well, to figure out this question, we will also need to use the interior angle formula. And so here we have the interior angle formula, n minus 2 times 180 degrees divided by n. So n is the amount of sides the figure has. So when we count up the sides, we get a total of 9. So we got 1, 2, 3, 4, 5, 6, 7, 9. And we use that 9 to go ahead and plug in for n to get n minus 2 times 80 divided by 9. And this thing will go, there we go. We get simply 140 degrees. So this obtuse angle right there is going to be 140 degrees. There's 140 degrees right there. And we can also use the central angle formula, 360 degrees divided by n, to figure out what that interior angle is right there. So we have 40 degrees right there. We have 140 degrees right there. 140 degrees is the interior angle formula, and we use the central angle formula to find out for that 40 degree. So going over to Jared's, I have a question for you, man.
Go for it.
How is the sum of interior angles discovered?
Well, thank you for asking. Yeah. Oh. Well, let's start off by creating our own n-gon. Let's say we have a pentagon here with 5 sides. Well, we want to start off by the total number of exterior angles is going to be 360 degrees. So with that in mind, we want to count up all the sides of the interior angles, in which case we have 1, 2, 3, 4, 5, 5 sides to this n-gon, so a 5-gon, so a pentagon. So we're going to take that and multiply it by 180. That is 180, 360, 540, 720, 1080. We need to take away 360, which represents the round of the exterior of the angle, to get 540 degrees. And that's how you find the sum of the interior angles. Start off with how many sides, multiply that by 180, and take away 360 degrees. That's how you do it. Now, Courtney, going back to you, how can you explain the process behind figuring out the angles in this figure here?
Thank you for asking. In this figure, we have 4 angles that are given. So I wrote down the 4 angles so we know what they are. We have BXD is equal to 90 degrees, AXE is 180, BXC is 35, and BXE is 128. For our first measure, we're trying to find the degree of AXB. And since we know the angle BXE is 128 and the angle of AXE is 180, we can subtract 128 from 180 and we'll get 52 for angle AXB. The second angle, we're trying to figure out the measurement of angle CXD. And since we know the angle BXC and the angle BXD, we will plug in the values. So CXD plus 35 equals 90 degrees, sorry. So 35 minus 90 is 55, so angle CXD is equal to 55. And the last angle we're trying to find is angle DXE. We know angle BXD is 90 degrees and angle BXE is 128. So when we subtract 90 from 128, we're going to get 38. And the angle DXE is equal to 38. And our next question is for Destiny. Destiny, how would you inscribe a tetrahedron inside of a cube at vertices D, E, B, and G without any of the faces touching?
That's a good question, Courtney. Thank you. In geometry, an inscribed planar shape or solid is an enclosed and it fits snugly inside of another figure. So that's what it means to be inscribed. So the first step to inscribing a tetrahedron inside of a cube would be to first, of course, construct your cube. And this is what our cube will look like. There we go. And this cube has vertices A, B, C, D, E, F, G, and H. Now, the next step is going to be in a different color to inscribe your tetrahedron on vertices D, E, B, and G, which looks something like this. And we have to make sure that the faces of the tetrahedron are subsets of the faces of the cube. And this means that none of the faces of the tetrahedron will be touching the cube. So for example, if you look at the face DEB of the tetrahedron, it's sharing some of the same vertices with the cube, but it's not touching or sharing or being snug with the face of the cube A, B, C, and D. So because it's true for this face of the tetrahedron, it's also going to be true for the other faces of the tetrahedron. So therefore, this is how you would draw a tetrahedron inside of a cube without any of the faces touching each other.
Good job.
So next on to Andrew. Can you count the faces of the tetrahedron inscribed inside of the cube?
Yes. Just as you previously said, tetra does mean 4. Therefore, this means that tetrahedron is a solid figure that has 4 plane triangular faces. Or in other thoughts, it can be seen as a triangular pyramid. So all we're going to do here is simply just count the sides. With all this crazy hectic math stuff, we need a question that we can just take a break from and just kind of count and understand what a tetrahedron and how much faces of a tetrahedron inside the cube has. So we're going to count how many. Can y'all see my mouse right here?
Yes.
Okay, so we have 1 right here, 2 right here, and then 3, and then 4 right there. So that's how many faces are in a tetrahedron. Always remember that it always has 4 plane triangular faces. Or in other thoughts, it can be seen as a triangle. Question for you.
All right.
What is the difference between interior and exterior angles?
Well, I'm glad you asked. All right. Well, let's start off by counting up the. Oh, snap. Look at the time. Oh, man. Yo, we're almost out of time. We have 6.5 minutes left. All right. Sorry about that hiccup. Anyhow, for an interior angle, you want to focus on the whole of the area that we have here. And the interior angles focus on the angles at each side. Remember our formula here. And the exterior angles pretty much focus on the outside of the polygon. And when it sticks out like this, it is also the same as the outside of the polygon. Andrew, or Courtney, I'm sorry. How would you find the measure of the interior angles in these triangles?
So we have 2 triangles. The first triangle we have the given degree of 38. And we know that a triangle will equal to 180. So we will subtract 38 from 180 to get 142. And we'd have 2x, because we added together the other 2 angles to get 2x. So we will divide 142 by 2 and get 71. So these 2 angles, x, will equal 71. The next triangle, we have, oh, it's okay. Y plus 2y plus 45 equals 180. We will subtract 45 by 180 to get 135. Putting together the equation, we will get y plus 2y equals 138. We will add together the y's to get 3y. Divide by 3, we'll get y equals 45. So this y equals 45 and 2y equals 90. Okay, Destiny, what is an octahedron?
Well, in order to determine the meaning of an octahedron, let's look at the prefix first. The prefix is octa, and this means that octa means 8. So you can probably guess how many sides an octahedron will have after knowing the prefix. So this is an image of an octahedron. And an octahedron, it's a 3-dimensional shape that has 8 equal triangular plane faces within it. So let's go ahead and count the faces. So this is 1, 2, 3, 4, 5, 6, 7, and this face right here is the 8th face. Thanks, Courtney.
Good job.
All right, Andrew, with the provided figures, how can we distinguish between what's a tetrahedron, octahedron, and an icosahedron?
Simple. All we have to do is look at how many faces it has, and what we're going to do, we're just going to go ahead and count these. Can you all see my mouse right here?
Yes.
Okay,
Yes.
so which one would be the tetrahedron? So it would actually be the far left because there is 4 faces. You got one big one and then 3 smaller ones in here. And the icosahedron is actually this middle one right here. It's this middle one. It has 20 faces if we have time to count. And the last one is an octahedron. It has 8. It has 8 equal faces. So this is the difference. They may look the same, but they have different amount of faces. But I have a question for you, Jared. What is a tetrahedron, and how does it relate to the figures that were drawn in the problem 5?
Well, y'all explained it perfectly, probably better than I could. Tetrahedron is kind of the triangle that we showed that has the 3 individual faces. Y'all drawed it out for here on the right. As you can see, the triangle each has 3 faces, and that's kind of what I want y'all to represent, is to see how to set up this multi-dimensional cube to show each individual face of the tetrahedron. So that's pretty much how it went. Courtney, we're going to wrap it up with you. How many different regions in the plane are determined by the figure?
We have a figure here, and we just have to count the faces. We have 1, 2, 3, 4, 5, 6.
All right.
And 7 for the overall figure. And there you'll kind of see it laid out. And that is all.
Thank y'all so much.
Thank you.
Thank
Have
you.
a good night.
Okay.